Let us next study the significance of Euler, Froude and Reynolds number introduced earlier. P naught divided by rho V naught square is 1 over Euler number, GD by V naught square is 1 over Froude number squared, and mu divided by rho V naught D is 1 over Reynolds number. Let's first start with Euler number. Note that it is not the pressure that appears in the governing equations, but its gradient. Therefore, the pressures may be measured with P naught as the datum, and we can work with gauge pressure Pg is equal to P minus P naught. If we do this, the equation is unaffected. This Pg is a pressure difference and does not require a characteristic pressure, but requires a characteristic pressure difference for normalization. To write a characteristic pressure difference, we need pressures at 2 points. However, in this problem, there is only one pressure P naught specified, and there is no other pressure specified. So, let us assume that the characteristic pressure difference is delta P sub naught, which is as yet unknown. If we make the changes, the equation that we started with changes into this second equation, and the pressure boundary condition becomes Pg star tends to 0. The gauge pressure non-dimensionalized tends to 0. So if we do this, then pressure P naught does not occur anywhere in this equation. Instead, a delta P naught has been introduced. If the pressure forces within a flow field are to be significant, that is, they are not negligible, the pressure force term in the equation should be of the same order as the inertial term. Thus, the coefficient of the pressure gradient term should be of order 1. This should be order 1. This is possible if the characteristic pressure difference delta P naught is of order rho V naught square. And so, we set customarily delta P naught is equal to 1/2 rho V naught square. And with this, the equation that governs the fluid flow becomes this. Now, there are only 2 parameters there. The Euler number is no longer relevant. Then we can write V star as a function of x star, the non-dimensional space point, and the parameters GD by V naught square and mu by rho V naught D, and the non-dimensional geometry. But this thing breaks down if 2 pressures are specified in the problem. Because if there are 2 specified pressure in the problem, then they would determine what a characteristic pressure difference is. So we can no longer set it arbitrarily at rho V naught square by 2. In that case, we will use that pressure difference. The 2 given pressures, the difference of those pressures would be the characteristic pressure difference. One such case is the flow of liquid with cavitation. Cavitation occurs whenever the pressure falls below the vapor pressure of the liquid. Thus, the difference P naught minus vapor pressure PV forms an independent characteristic pressure difference, and the Euler number has to be defined as rho V naught square divided by rho P naught minus PV. And this Euler number needs to be matched in model and the prototype flows. Next, we consider GD by V naught square. It is possible in some cases to redefine the problem in such a manner that the fluid number similarity can also be eliminated as a modeling requirement. We introduce a new variable, a modified pressure, written as script P, defined as P plus rho Gz minus P naught. It may be noted that this modified pressure has a constant value throughout a stationary fluid. And it is for this reason that this is called the non-gravitational gauge pressure. And if we introduce this, the first two terms of the governing equation combine into a single term. The pressure condition has now changed to the non-dimensional modified pressure tending to 0 on Z star is equal to 0 as X star tends to minus infinity. Only Reynolds number and the modified Euler number rho V naught square divided by delta P naught have to be matched. If in addition the flow conditions are such that only one pressure P naught is specified, we can take delta P naught is equal to rho V naught square by 2 as the characteristic pressure difference, and then only Reynolds number needs to be matched. However, this simplification is not always possible. For example, in problems involving a free surface of the liquid, like shown here, and this shape changes with motion. The free surface is specified as Z is equal to ZF X, and the pressure at this point is P naught everywhere. So, the boundary condition is replaced by P is equal to P naught at Z is equal to ZF. When the non-gravitational gauge pressure script P gauge is introduced, the pressure boundary condition in this case is modified as Pg is equal to rho G ZF at Z is equal to ZF, which our non-dimensional gives this. Now notice that G, which does not appear in the equation of motion, has now appeared in the boundary condition. Thus, gravity effects are important in problems with free surface. Such conditions occur, for example, in the motion of ships and other vessels close to the surface of ocean. Similarly, fluid number in the models must be same as the fluid number in the prototypes in flows over dams, weirs, and in open channels. However, fluid number may be ignored as a similarity requirement for submarine operating at large depths far away from the free surface. Let's do one example: cavitation on torpedoes fins. You see, when a torpedo is moving under sea, what happens is that on fins the velocity increases and so the pressure decreases. As the pressure decreases below the vapor pressure at that temperature, then a vapor bubble is formed. Those vapor bubbles have a tendency that as the pressure increases back, if the fluid slows down when move away from the fin, the pressure increases, the vapor bubbles, the diameter of the vapor bubbles decreases, then the vapor bubble splits and suddenly a jet impinges on the surface. And this jet can cause erosion and pitting on the surfaces of fin surfaces, which will decrease the control of the vehicle. So we need to avoid cavitation. A torpedo of diameter 20 centimeters is seen to be on the verge of cavitation at a speed of 30 meters per second when running 10 meters below the ocean surface. The temperature is 20 degrees Celsius. From this temperature, I can find out the vapor pressure. It's about 3.4 kilopascal. At what depth must the torpedo run if it is to travel 50 meters per second? If we want to run it faster, then the pressure difference would be larger. So if cavitation does not have to be occur, the ambient pressure should be larger. So depth of the torpedo run must be more. As 10 meters is fairly large compared to torpedo size, the Froude number does not need to be matched. And we replace P by script P is equal to P plus rho Gz minus P naught, the non-gravitational pressure difference. But since cavitation is involved, the Euler number with script P minus P at the cavitation pressure taken as the characteristic modified pressure is now to be matched. So we have to match these two for prototype and model. Script P naught minus script P V is like this at reference pressure P naught and at cavitation. Taking the datum at the ocean surface, P is equal to P naught and Z is equal to 0, we get this value is equal to P naught minus PV minus rho Gz. So this for the model is, we plug in the value and we get 200 kilopascal. Equivalence of Euler number then results in this expression as the modeling rule. Euler number must be same. So the characteristic pressure difference in the prototype should be characteristic pressure difference in the model multiplied by the velocity in the prototype divided by velocity in the model whole squared. And this gives you that the characteristic pressure difference in the prototype should be 555.7 kilopascal as against 200 kilopascal in the model. And this is obtained at the depth of 45.2 meters. Thank you very much.